Hello. Today I am Professor Rose, here to bore you to sleep with a long math lecture about fractions. Suppose it is required to divide 49 yards into 5 equal parts, or as it is called, to find the 5th part of 49 yards. If we divide 45 by 5, the quotient is 9, and the remainder is 4. That is, 49 is made up of 5 9 times and 4. Take 5 lines C, D, E, F, and G, each 9 yards in length, and the line H, 4 yards in length. Then, since 49 is 5 9s and 4, C, D, E, F, G, and H are together equal to A, B. Divide H, which is 4 yards, into 5 equal parts, I, K, L, M, and N, and place one of these parts opposite to each of the lines C, D, E, F, and G. It follows that the 10 lines C, D, E, F, G, I, K, L, M, N are together equal to A, B, or 49 yards. Now, D and K together are of the same length as C and I together, and so are E and L, F and M, and G and N. Therefore, C and I together, repeated 5 times, will be 49 yards. That is, C and I together make up the 5th part of 49 yards. C is a certain number of yards, but I is a new sort of quantity to which hitherto we have never come. It is not an exact number of yards, for it arises from dividing 4 into 5 parts and taking 1 of those parts. It is the 5th part of 4 yards and is called a fraction of a yard. It is written 4/5 and is what we must add to 9 yards in order to make up the 5th part of 49 yards. The same reasoning would apply to dividing 49 bushels of corn or 49 acres of land into 5 equal parts. We should find for the 5th part of the first 9 bushels, and the 5th part of 4 bushels. For the second, 9 acres, and the 5th part of 4 acres. We say, then, once for all, that the 5th part of 49 is 9 4/5, or 9 plus 4/5. Or if we use signs, 49/5 equals 9 4/5. Exercises. What is the 17th part of 1, 2, 3, 7? Answer: 72 and 13/17. What are 10032 over 1974? 663,819 over 23710 and 2277339 over 2424. Answer: 5 and 162 over 1974. 27 and 23649 over 2339 710 and 9394 and 2343 over 2424. By the term fraction is understood a part of any number or the sum of any of the equal parts into which a number is divided. Thus, 9 over 5, 4 over 5, 20 over 7 are fractions. The term fraction even includes whole numbers. For example, 17 is 17 over 1. 34 over 2. 51 over 3. And so on. The upper number is called the numerator. The lower number is called the denominator, and both of these are called terms of the fraction. As long as the numerator is less than the denominator, the fraction is less than a unit. Thus, 6 over 17 is less than a unit, for 6 divided into 6 parts gives 1 for each part, and must give less when divided into 17 parts. Similarly, the fraction is equal to a unit when the numerator and denominator are equal, and greater than a unit when the numerator is greater than the denominator. By 2 over 3 is meant the third part of 2. This is the same as twice the third part of 1. To prove this, let A, B be 2 yards, and divide each of the yards A, C, and C, B into 3 equal parts. Then, because A, E, E, F, AE is the third part of 2. It is therefore 2 over 3. But AE is twice AD, and AD is the third part of 1 yard, or 1/3. Therefore, 2/3 is twice 1/3. That is, in order to get the length 2 over 3, it makes no difference whether we divide 2 yards at once into 3 parts and take 1 of them, or whether we divide 1 yard into 3 parts and take 2 of them. By the same reasoning, 5 over 8 may be found either by dividing 5 into 8 parts and taking 1 of them, or by dividing 1 into 8 parts and taking 5 of them. In future, of these 2 meanings, I shall use that which is most convenient at the time, as it is proved that they are the same thing. This principle is the same as the following. The third part of any number may be obtained by adding together the thirds of all the units of which it consists. Thus, the third part of 2, or of 2 units, is made by taking 1/3 out of each of the units. That is, 2 over 3 equals 1 over 3 times 2. This meaning appears ambiguous when the numerator is greater than the denominator. Thus, 15 over 7 would mean that 1 is to be divided into 7 parts, and 15 of them are to be taken. We should here let as many units be each divided into 7 parts, as will give more than 15 of those parts, and take 15 of them. The value of a fraction is not altered by multiplying the numerator and denominator by the same quantity. Take the fraction 3/4. Multiply its numerator and denominator by 5, and it becomes 15/20, which is the same thing as 3/4. That is 1/20th part of 15 yards is the same thing as 1/4 of 3 yards, or if our second meaning of the word fraction be used, you get the same length by dividing a yard into 20 parts and taking 15 of them, as you get by dividing it into 4 parts and taking 3 of them. To prove this, let AB represent a yard. Divide it into 4 equal parts: AC, CD, DE, and EB, and divide each of these parts into 5 equal parts. Then AE is 3/4. But the second division cuts the line into 20 equal parts, of which AE contains 15. It is therefore 15/20. Therefore, 15/20 and 3/4 are the same thing. Again, since 3/4 is made from 15/20 by dividing both the numerator and denominator by 5, the value of a fraction is not altered by dividing both its numerator and denominator by the same quantity. This principle, which is of so much importance in every part of arithmetic, is often used in common language, as when we say 14 out of 21 is 2 out of 3, and so on. Though the two fractions 3/4 and 15/20 are the same in value, and either of them may be used for the other without error, yet the first is more convenient than the second, not only because you have a clearer idea of the 1/4 of 3 yards than of the 20th part of 15 yards, but because the numbers in the first, being smaller, are more convenient for multiplication and division. It is therefore useful when a fraction is given to find out whether its numerator and denominator have any common divisors or common measures. Above, it was given as a rule for finding the greatest common measure of any two numbers, and it was shown that when the two numbers are divided by their greatest common measure, the quotients have no common measure except 1. Find the greatest common measure of the terms of the fraction and divide them by that number. The fraction is then said to be reduced to its lowest terms, and is in the state in which the best notion can be formed of its magnitude. Exercises. With each fraction is written the same, reduced to its lowest terms. 2, 7, 9, 4 over 2, 9, 2, 1 equals 22 times 1, 2, 7 over 23 times 1, 2, 7 equals 22 over 23. 2, 7, 8, 8 over 4, 9, 2, 0 equals 17 times 1, 6, 4 over 30 times 1, 6, 4 equals 17 over 30. 9, 3, 2, 8, 0 over 1, 3, 7, 8, 6 equals 7, 6, 4 times 1, 2, 2 over 1, 1, 3 times 1, 2, 2 equals 7, 6, 4 over 1, 1, 3. 8, 8, 8, 8, 0, 0 over 4, 0, 3, 5, 9, 6, 0, 0 equals 2, 2 times 4, 0, 4, 0, 0 over 9, 9, 9 times 4, 0, 4, 0, 0 equals 2, 2 times 9, 9, 9. 9, 5, 4, 6, 9 over 3, 5, 9, 7, 8, 4 equals 1, 2, 1 times 7, 8, 9 over 4, 5, 6 times 7, 8, 9 equals 1, 2, 1 over 4, 5, 6. When the terms of the fraction given are already in factors, any one factor in the numerator may be divided by a number provided some one factor in the numerator is divided by the same. This follows from above. In the following examples, the figures altered by division are accented with a prime. 12 times 11 times 10 over 2 times 3 times 4 equals 3 prime times 11 times 10 over 2 times 3 times 1 prime equals 1 prime times 11 times 5 prime over 1 prime times 1 prime times 1 prime equals 55. 18 times 15 times 13 over 20 times 54 times 52 equals 2 prime times 3 prime times 1 prime over 4 prime times 6 prime times 4 prime equals 1 prime times 1 prime times 1 prime over 2 prime times 2 prime times 4 prime equals 1 over 16. 27 times 28 over 9 times 70 equals 3 prime times 4 prime over 1 prime times 10 prime equals 3 prime times 2 prime over 1 prime times 5 prime equals 6 over 5. As we can see, we multiply the numerator and denominator of a fraction by any number without altering its value. We can now readily reduce two fractions to two others, which shall have the same value as the first two, and which shall have the same denominator. Take, for example, 2 over 3 and 4 over 7. Multiply both terms of 2 over 3 by 7 and both terms of 4 over 7 by 3, it then appears that 2 over 3 is 2 times 7 over 3 times 7, or 14 over 21. 4 over 7 is 4 times 3 over 7 times 3, or 12 over 21. Here are, then, two fractions: 14 over 21 and 12 over 21, equal to 2 over 3 and 4 over 7, and having the same denominator, 21. In this case, 2 over 3 and 4 over 7 are said to be reduced to a common denominator. It is required to reduce 1 over 10, 5 over 6, and 7 over 9 to a common denominator. Multiply both terms by the first product of 6 and 9, of the second by the product of 10 and 9, and of the third by the product of 10 and 6. Then it appears that 1 over 10 is 1 times 6 times 9 over 10 times 6 times 9, or 54 over 540. 5 over 6 is 5 times 10 times 9 over 6 times 10 times 9, or 540 over 450. 7 over 9 is 7 times 10 times 6 over 9 times 10 times 6, or 420 over 540. On looking at these last fractions, we see that all the denominators and common numerators are divisible by 6. And this division will not alter their values. On dividing the numerators and denominators of 5, 4 over 5, 4, 0, 4, 5, 0 over 5, 4, 0, and 4, 2, 0 times 5, 4, 0 by 6. The resulting fractions are 9 over 9, 0, 7, 5 over 9, 0, and 7, 0 over 9, 0. These are fractions with a common denominator, and which are the same as 1 over 10, 5 over 6, and 7 over 9. And therefore, these are a more simple answer to the question than the first fractions. Observe also that 5, 4, 0 is one common multiple of 10, 6, and 9, namely 10 times 6 times 9, but that 90 is the least common multiple of 10, 6, and 9. The following process, therefore, is better. To reduce the fractions 1 over 10, 5 over 6, and 7 over 9, to others having the same value and a common denominator, begin by finding the least common multiple of 10, 6, and 9 by the rule above, which is 90. Observe that 10, 6, and 9 are contained in 90. 20, 9, 15, and 10 times. Multiply both terms of the first by 9, of the second by 15, and of the third by 10, and the fractions thus produced are 9 over 9, 0, 7, 5 over 9, 0, 7, 0 over 9, 0, the same as before. If one of the numbers be a whole number, it may be reduced to a fraction, having the common denominator of the rest. By reducing two fractions to a common denominator, we are able to compare them. That is, to tell which is the greater and which the less of the two. For example, take 1 over 2 and 7 over 15. These fractions reduced without alteration of their value to a common denominator are 15 over 30 and 14 over 31. Of these, the first part must be greater because it may be obtained by dividing 1 into 30 equal parts and taking 15 of them. But the second is made by taking 14 of those parts. It is evident that of two fractions which have the same denominator, the greater has the greater numerator, and also that of two fractions which have the same numerator, the greater has the less denominator. Thus, 8 over 7 is greater than 8 over 9, since the first is a seventh, and the last only a ninth part of 8. Also, any numerator may be made to belong to as small a fraction as we please by sufficiently increasing the denominator. Thus, 10 over 1 over 10. 10 over 1,000 is 1 over 100, and 10 over 1,000,000 is 1 over 100,000. We can now also increase and diminish the first fraction by the second. For the first fraction is made up of 15 of the 30 equal parts into which one is divided. The second fraction is 14 of those parts. The sum of the two, therefore, must be 15 plus 14, or 29 of those parts. That is 1 over 2 plus 7 over 15 is 29 over 30. The difference of the two must be 15 minus 14, or 1 of those parts. That is 1 over 2 minus 17 over 15 equals 1 over 30. From the last two articles, the following rules are obtained. To compare, to add, or to subtract fractions, first reduce them to a common denominator. When this has been done, that is the greatest of the fractions, which has the greatest numerator. Their sum has the sum of the numerators for its numerator, and the common denominator for its denominator. Their difference has the difference of the numerators for its numerator, and the common denominator for its denominator. Exercises. 1 over 2 plus 1 over 3 plus 1 over 4 minus 1 over 5 equals 53 over 60. 44 over 3 minus 153 over 430 27 equals 18329 over 1282. 1 plus 8 over 10 plus 3 over 100 minus 4 over 1000 equals 1834 over 1000. 2 minus 1 over 7 plus 12 over 13 equals 253 over 9 1. 1 over 2 plus 8 over 16 plus 9 4 over 1 8 8 equals 3 over 2. 1 6 3 over 5 2 1 minus 9 7 over 8 8 1 equals 9 3 0 6 6 over 4 5 9 0 0 1. Suppose it required to add a whole number to a fraction. For example, 6 to 4 over 9 by 6 is 5 4 over 9 and 5 4 over 9 plus 4 over 9 is 5 8 over 9. That is 6 plus 4 over 9, or as it is usually written, 6 and 4 over 9 is 5 8 over 9. The rule in this case is multiply the whole number by the denominator of the fraction, and to the product add the numerator of the fraction. The sum will be the numerator of the result, and the denominator of the fraction will be its denominator. Thus, 3 and 1 over 4 equals 13 over 4. 22 and 5 over 9 equals 203 over 9. 74 and 2 over 55 equals 4072 over 55. This rule is the opposite of that above. From the last rule, it appears that 1, 7, 2, 3 and 9, 0, 7 over 10,000 is 1, 7, 2, 3, 0, 9, 0, 7 over 10,000. 6, 6, 7 and 2, 2, 5 over 1,000 is 6, 6, 7, 2, 2, 5 over 1,000. And 23 and 9, 9 over 10,000 is 2, 3, 0, 0, 0, 9, 9 over 10,000. Hence, when a whole number is to be added to a fraction whose denominator is 1, followed by ciphers, the number of which is not less than the number of figures in the numerator. The rule is write the whole number first, and then the numerator of the fraction, with as many ciphers between them as the number of ciphers in the denominator exceeds the number of figures in the numerator. This is the numerator of the result, and the denominator of the fraction is its denominator. If the number of ciphers in the denominator be equal to the number of figures in the numerator, write no ciphers between the whole number and the numerator. Exercises. Reduce the following mixed quantities to fractions. 1 and 2, 3, 7, 0, 7 over 100,000. 2, 4, 5, 7 and 6 over 10. 2, 3, 3 and 2, 2, 1, 0 over 10,000. Suppose it is required to multiply 2 over 3 by 4. This is taking 2 over 3 4 times. That is, finding 2 over 3 plus 2 over 3 plus 2 over 3 plus 2 over 3. This is 8 over 3. So that to multiply a fraction by a whole number, the rule is multiply the numerator by taking the whole number and let the denominator remain. If the denominator of the fraction be divisible by the whole number, the rule may be stated thus: divide the denominator of the fraction by the whole number and let the numerator remain. For example, multiply 7 over 36 by 6. This is 42 over 36, which, since the numerator and denominator are now divisible by 6, the same as 7 over 6. It is plain that 7 over 6 is made from 7 over 36 in the manner stated in the rule. Multiplication has been defined to be the taking as many of one number as there are units in another. Thus, to multiply 12 by 7 is to take as many 12s as there are units in 7, or to take 12 as many times as you must take 1 in order to make 7. Thus, what is done with 1 in order to make 7 is done with 12 to make 7 times 12. For example, 7 is 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1. 7 times 12 is 12 plus 12 plus 12 plus 12 plus 12 plus 12 plus 12. When the same thing is done with 2 fractions, the result is still called their product, and the process is still called multiplication. There is this difference. Whereas a whole number is made by adding 1 to itself a number of times, a fraction is made by dividing 1 into a number of equal parts and adding one of these parts to itself a number of times. This being the meaning of the word multiplication as applied to fractions. What is 3 over 4 multiplied by 7 over 8? Whatever is done with 1 to make 7 over 8 must now be done with 3 over 4. But to make 7 over 8, 1 is divided into 8 parts, and 7 of them are taken. Therefore, to make 3 over 4 times 7 over 8, 3 over 4 must be divided into 8 parts, and 7 of them must be taken. Now, 3 over 4 is the same thing as 2, 4 over 3, 2. Since 2, 4 over 3, 2 is made by dividing 1 into 32 parts and taking 24 of them, or, which is the same thing, taking 3 of them 8 times. If 24 over 32 be divided into 8 equal parts, each of them is 3 over 32. And if 7 of these parts be taken, the result is 21 over 32. Therefore, 3 over 4 multiplied by 7 over 8 is 21 over 32. And the same reasoning may be applied to any other fractions. But 21 over 32 is made from 3 over 4 and 7 over 8 by multiplying the two numerators together for the numerator and the two denominators for the denominator, which furnishes a rule for the multiplication of fractions. If this product, 21 over 32, is to be multiplied by a third fraction, for example, by 5 over 9, the result is, by the same rule, 105 over 288, and so on. The general rule for multiplying any number of fractions together is, therefore, multiply all the numerators together for the numerator of the product and all the denominators together for its denominator. Suppose it required to multiply together 15 over 16 and 8 over 10. The product may be written thus: 15 times 8 over 16 times 10 and is 120 over 160, which reduced to its lowest terms is 3 over 4. This result might have been obtained directly by observing that 15 and 10 are both measured by 5, and 8 and 16 are both measured by 8, and that the fraction may be written thus: 3 times 5 times 8 over 2 times 8 times 2 times 5. Divide both its numerator and denominator by 5 times 8, and the result is at once 3 over 4. Therefore, before proceeding to multiply any number of fractions together, if there be any numerator and any denominator, whether belonging to the same fraction or not, which have a common measure, divide them both by that common measure and use the quotients instead of the dividends. A whole number may be considered as a fraction whose denominator is 1. Thus, 16 is 16 over 1. And the same rule will apply when one or more of the quantities are whole numbers. Exercises 1, 3, 6 over 7, 4, 7, 0 times 2, 6, 8 over 9, 1, 9 equals 3, 6, 4, 4, 8 over 6, 8, 6, 4, 9, 3, 0 equals 1, 8, 2, 2, 4 over 3, 4, 3, 2, 4, 6, 5. 1 plus 2 times 2 over 3 times 3 plus 4 1 over 5. 2 over 17 times 17 over 45 equals 2 times 45. 2 over 59 times 13 over 7 times 2, 4, 1 over 19 equals 6, 2, 6, 6 over 7, 8, 7, 4. 1, 3 over 4, 6, 1 times 6, 0, 1 over 11 equals 7, 8, 1, 3 over 5, 0, 7, 1. Fraction proposed. 7, 0, 1 over 1, 5, 8. Square. 4, 9, 1, 4, 0, 1 over 2, 4, 9, 6, 4. Cube. 3, 4, 4, 4, 7, 2, 1, 0, 1 over 3, 9, 4, 4, 3, 1, 2. Fraction proposed. 1, 4, 0 over 1, 4, 1. Square. 1, 9, 6, 0, 0 over 1, 9, 8, 8, 1. Cube. 2, 7, 4, 4, 0, 0, 0 over 2, 8, 0, 3, 2, 2, 1. Fraction proposed. 3, 5, 5 over 1, 1, 3. Square. 1, 2, 6, 0, 2, 5 over 1, 2, 7, 6, 9. Cube. 4, 4, 7, 3, 8, 8, 7, 5 over 1, 4, 4, 2, 8, 9, 7. From 100 acres of ground, 2/3 of them are taken away. 50 acres are then added to the result, and 5/7 of the whole is taken. What number of acres does this produce? Answer: 59 and 11/21. In dividing one whole number by another, for example, 108 by 9, this question is asked: can we, by the addition of any number of 9s, produce 108? And if so, how many 9s will be sufficient for this purpose? Suppose we take two fractions, for example, 2/3 and 4/5, and ask, can we, by dividing 4/5 into some number of equal parts, and adding a number of these parts together, produce 2/3? If so, into how many parts must we divide 4/5? And how many of them must we add together? The solution of this question is still called the division of 2/3 by 4/5. And the fraction whose denominator is the number of parts into which 4/5 is divided, and whose numerator is the number of them which is taken, is called the quotient. The solution of this question is as follows. Reduce both these fractions to a common denominator, which does not alter their value. They then become 10/15 and 12/15. The question now is to divide 12/13 into a number of parts, and to produce 10/15 by taking a number of these parts. Since 12/15 is made by dividing 1 into 15 parts and taking 12 of them, if we divide 12/15 into 12 equal parts, each of these parts is 1/15. If we take 10 of these parts, the result is 10 over 15. Therefore, in order to produce 10 over 15, or 2 over 3, we must divide 12 over 15 into 12 parts and take 10 of them. That is, the quotient is 10 over 12. If we call 2 over 3 the dividend and 4 over 5 the divisor, as before, the quotient in this case is derived from the following rule, which the same reasoning will show to apply to other cases. The numerator of the quotient is the numerator of the dividend multiplied by the denominator of the divisor. The denominator of the quotient is the denominator of the dividend multiplied by the numerator of the divisor. This rule is the reverse of multiplication, as will be seen by comparing what is required in both cases. In multiplying 4 over 5 by 10 over 12, I ask if out of 4 over 5 be taken 10 parts out of 12, how much of a unit is taken? And the answer is 40 over 60, or 2/3. Again, in dividing 2/3 by 4/5, I ask what part of 4/5 is 2/3. The answer to which is 10 over 12. By taking the following instance, we shall see that this rule can be sometimes simplified. Divide 16 over 33 by 28 over 15. Observe that 16 is 4 times 4, and 28 is 4 times 7. 33 is 3 times 11, and 15 is 3 times 5. Therefore, the two fractions are 4 times 4 over 3 times 11, and 4 times 7 over 3 times 5. And their quotient, according to the rule, is 4 times 4 times 3 times 5 over 3 times 11 times 4 times 7, in which 4 times 3 is found both in the numerator and denominator. The fraction is therefore the same as 4 times 5 over 11 times 7, or 20 over 77. The rule of the last article, therefore, admits of this modification. If the two numerators or the two denominators have a common measure, divide by that common measure and use the quotients instead of the dividends. In dividing a fraction by a whole number, for example, 2 over 3 by 15, consider 15 as the fraction 15 over 1. The rule gives 2 over 45 as the quotient. Therefore, to divide a fraction by a whole number, multiply the denominator by that whole number. Exercises. Dividend 41 over 33. Divisor 63 over 11. Quotient 41 over 189. Dividend 467 over 151. Divisor 907 over 101. Quotient 4717 over 136,957. Dividend 7813 over 5071. Divisor 601 over 11. Quotient 13 over 461. What are 1 over 5 times 1 over 5 times 1 over 5 minus 2 over 17 times 2 over 17 times 2 over 17 all over 1 over 5 minus 2 over 17 and 8 over 11 times 8 over 11 minus 3 over 11 times 3 over 11 all over 8 over 11 minus 3 over 11. Answers: 5, 5, 9 over 7, 2, 2, 5 and 1. A can reap a field in 12 days. B in 6 and C in 4 days. In what time can they do it all together? Answer: 2 days. In what time would a cistern be filled by clocks which would separately fill in 12, 11, 10, and 9 hours? Answer: 2 and 4, 5, 4 over 7, 6, 3 hours. The principal results of this section may be exhibited algebraically as follows. Let A, B, C, and so on stand for any whole numbers. Then A over B equals 1 over A times A. A over B equals M-A times M-A. A over B and C over D are the same as A D over B D and B C over B D. A over C plus B over C equals A plus B over C. A over C minus B over C equals A minus B over C. A over B plus C over D equals A plus B C over B D. A over B minus C over D equals A D minus B C over B D. A over B times C over D equals A C times B D. These results are true even when the letters themselves represent fractions. For example, take the fraction A over B all over C over D, whose numerator and denominator are fractional, and multiply its numerator and denominator by the fraction E over F, which gives AE over BF over CE over DF, which is AEDF over BFCE, which, dividing the numerator and denominator by EF, is AD over BC. But the original fraction itself is AD over BC. Hence, A over B over C over D equals A over B times E over F all over C over D times E over F, which corresponds to the second formula. In 124, in a similar manner, it may be shown that the other formula of the same article are true when the letters there used either represent fractions or are removed and fractions introduced in their place. All formula established throughout this work are equally true when fractions are substituted for whole numbers. For example, m plus n times a equals m times a plus n times a. Let m, n, and a be respectively the fractions p over q, r over s, and b over c. Then m plus n is p over q plus r over s, or p PS plus QR over QS. And M times N plus A is PS plus QR all over QS times B over C, or PS plus QR times B all over QSC, or PSB plus QRB all over QSC. But this is PSB over QSC plus QRB over QSC, which is PB over QC plus RB over SC, since PSB over QSC equals PB over QC, and QRB over QSC equals RB plus SC. But PB over QC equals P over Q, and B over C times RB over SC equals R over S times B over C. This concludes our lesson on fractions today. Thank you so very much for watching.